Hi everyone. Today we're going to be completing our notes on graphing rational functions. Now I want to start just by defining what is a rational function. A rational function is simply a polynomial over a polynomial. So it's the ratio of two polynomial functions. So everything that we learned previously about polynomials, like with end behavior, with zeros and roots, with multiplicity of those zeros, all of those things that we learned for polynomials is going to be true here for rational functions. However, there's a few additional properties that we get from taking the ratio of two polynomial functions. Let's start with looking at end behavior asymptotes. So example 1, here I have the rational function y equals the quantity x plus 1 over the quantity x plus 3. We can see that as we approach the left-hand side of this function, as x approaches negative infinity, the function approaches a particular y value. In this case, it approaches y equals 1. In the same vein, we have on the right-hand side, as x approaches positive infinity, the function approaches that same particular y value, y equals 1. And so we can write this using limit notation. The limit of the quantity x plus 1 over x plus 3 as x approaches negative infinity is equal to the finite value 1. Likewise, the limit of x plus 1 over x plus 3 as x approaches positive infinity is also equal to 1. Therefore, the equation of the end behavior asymptote is the horizontal line y equals 1. And we can see that on the graph as this dotted horizontal line here. For graph number 2, here we have the function f of x as this rational function here. The end behavior, it doesn't appear to be approaching a horizontal line. In this case, we've got this slanted line. And this slanted line is an asymptote. It's what the function approaches but never actually reaches. We would call this a slant asymptote. Another name for this type of asymptote is an oblique asymptote. And so the function on the right-hand side is going to approach this asymptote from the top side, and then on the left-hand side of the function, it's going to approach the asymptote from the bottom side. And so we can see that we'll say the limit of f of x as x approaches negative infinity is equal to negative infinity. This function, as we move to the left, is just going to keep decreasing, and it's never going to approach a finite value. It's just going to keep decreasing and approach negative infinity. In the same vein, we have the limit of f of x. As x approaches positive infinity, it's just going to blow up to infinity. It's just going to continue increasing. So then the equation of the end behavior asymptote is that slant asymptote, which is given to us y equals x plus 2. And later on in this unit, we're going to talk about how to find those equations for the slant asymptotes algebraically. So let's talk about dominant term for a moment. So similar to polynomials where the dominant term is just that leading term in standard form, or it's like that term with the highest exponent, we have something similar for rational functions. Remember, it's a polynomial over a polynomial. So what we can do is we can find the dominant terms of both the numerator and denominator. So in this first function, a of x, we find that the dominant term of the numerator is simply 3, and the dominant term of the denominator is x. So therefore, the left-hand end behavior is the same as that of the quantity 3 over x as x approaches negative infinity. And so this, as x approaches negative infinity, as we plug in increasingly negative numbers in for x, we find that the quantity 3 over x is a number that's very close to 0, but it's going to be negative. So a very, very tiny, tiny negative number. Well, as x approaches negative infinity, this is going to approach 0. On the right-hand side, the limit of 3 over x as x approaches positive infinity. As we plug in increasingly large values, large positive values for x, we have 3 over very large quantities. We have that this approaches 0 as well. So the end behavior asymptote, both the limits agree, so we have y equals 0. For b of x, we have that the dominant term in the numerator, we have x squared. The dominant term in the denominator, we've got 3 x's, so this would be x cubed. This reduces to 1 over x. So we can say that the end behavior is similar to that of 1 over x. And so the left-hand end behavior as x approaches negative infinity, this is similar to a of x. It's going to approach 0. Likewise, the right-hand end behavior, 1 over x, as x approaches infinity, is also going to approach 0. So that tells me my end behavior asymptote is also y equals 0. Finally, for c of x, we can see that the dominant term, we have 4x and x, so that tells us in the numerator the dominant term is 4x squared, and in the denominator we have 2x squared. So this reduces to simply 4 over 2, or 2. Okay? So the end behavior of this function is going to be the same as that of the constant value, y equals 2. And because this is an unchanging value that's independent of the variable x, the end behavior is going to be exactly that. It's going to be 2. So this function is going to approach the finite value y equals 2 as we approach both ends. So the limit of 2 as x approaches positive infinity, again, it's independent of x, so this approaches y equals 2. All right, so let's get a little bit of practice. Flip the page. For number 1, we're going to first use limit notation to describe the end behavior, and then we're going to write the end behavior asymptote. So here, the dominant terms are x over x squared, which reduces to 1 over x. So we have the limit of r of x as x approaches negative infinity is equal to 0. The limit of r of x as x approaches positive infinity is equal to 0 as well. So the equation for the end behavior asymptote is y equals 0. And finally, p of x, here we have our dominant term in the numerator is 3x squared, and our dominant term in the denominator is x squared. So this is going to approach the finite value 3. So the limit of p of x as x approaches negative infinity is equal to 3, and the limit of p of x as x approaches positive infinity is also 3. So the end behavior asymptote here is 3. Now, before we move on to vertical asymptotes, I want to just generalize a rule here. So notice that it has to do with the degrees of the dominant terms of the numerator and denominator. So what I notice is that if we're going to go ahead and define this. So we're going to say let n be the degree of the numerator, and then let m be the degree of the denominator. We have 3 cases. That should be denominator. Okay, so we have 3 cases. Case 1 is if it is, we're going to call it top heavy. Okay, so if the function is top heavy, we're saying that the degree of the numerator is greater than that of the denominator. So that's saying that this function would approach something similar to like y equals x or y equals x squared, anything that has a positive exponent here for the x. Okay, so that would tell us that the function is just going to blow up to infinity or negative infinity. So the limit of the function is going to approach plus or minus infinity. Okay. The case number 2 is if it's bottom heavy. Okay, so that's saying that the degree of the denominator is greater than that of the numerator. So this would be something similar to our 1 over x or 1 over x squared or 1 over x cubed, right? So it's bottom heavy. We have a greater degree in the denominator. The limit of the function, the end behavior, is going to approach 0. So our end behavior asymptote would be y equals 0. The last case is if n equals m. And so this would be like evenly weighted. Okay, and I'm putting all these in quotes. So this would be if the degrees are equal. Then it's simply the end behavior is just the ratio of the leading coefficients. Okay, so an example that we can see here is example 2. Oops, I forgot to write x squared here. So in example 2, we can see that the degree of both the numerator and denominator is 2. So therefore, we take the ratio of the leading coefficients, 3 over 1, which is 3. We can also see that similar example in c of x on the previous page. Degree is again the same, so the ratio of leading coefficients 4 over 2 is just 2. So end behavior asymptote is y equals 2. Okay, so these are going to be our 3 cases. That's going to help us define the end behavior of these rational functions. All right. So let's go ahead and talk about now vertical asymptotes. A vertical asymptote is an x value that makes the denominator 0. Or in other words, it's where the function is undefined. We've seen vertical asymptotes before, like, for example, when talking about logarithms. The function is undefined when the denominator is equal to 0. Okay? Another way that we might refer to this, vertical asymptotes, is an infinite discontinuity. Okay, so I'm going to use those terms interchangeably, a vertical asymptote and an infinite discontinuity. Okay, so for j of x, let's go ahead and find the equation for the vertical asymptote. So consider what would cause this rational function to be undefined. It's any time that we divide by 0. So where this denominator is equal to 0 is also where this function is undefined. So if we set the denominator equal to 0, solutions to that equation is where the function is undefined. So I'm going to go ahead and factor this. We have x minus 4 and x plus 2 is equal to 0. Setting each of those equal to 0 with the zero product property, we get the equations x equals 4 and x equals negative 2. And notice that these are equations for vertical lines. These are where the function is undefined. Okay, these are the vertical asymptotes. For r of x, it's where x squared minus 4 equals 0, the denominator. So we have the quantity x plus 2 times the quantity x minus 2 is equal to 0. So x plus 2 equals 0 or x minus 2 equals 0. So then we get the equations x equals negative 2 and x equals positive 2. So this function, r of x, has two vertical asymptotes, or two infinite discontinuities. Let's get some practice. G of x here, again, we're going to set that denominator equal to 0. So we have x squared minus 4x is equal to 0. Factoring this, we can factor out a GCF of x. So we get x times a quantity, x minus 4, is equal to 0. So we get the two equations, x equals 0 or x minus 4 equals 0. And so we have the two vertical asymptotes, x equals 0 and x equals 4. For h of x over here, we have x squared plus x minus 6 is equal to 0. And this factors to x plus 3 and x minus 2. Setting each of those equal to 0, we have x plus 3 equals 0 and x minus 2 equals 0. So x must equal negative 3 or x must equal 2. Okay. All right. Go ahead and flip the page. Last thing here is x and y intercepts. So x-intercepts, remember, an x-intercept is anywhere that y equals 0. So if y equals 0, we're talking about the function values. So in this first example, h of x, we're saying where h of x equals 0. So if a ratio of polynomial over another polynomial is equal to 0, that's the same as just saying that the numerator is equal to 0, because anything that would cause the numerator to be equal to 0 causes the entire function to be equal to 0. Okay? So the x-intercept, set the numerator equal to 0. For the y-intercept, just evaluate the function for x equals 0. Okay? So for h of x, let's go ahead and find x and y-intercepts. So we'll start with x-intercepts. So remember, that's where y equals 0 or where the numerator equals 0. So we're saying where the quantity x plus 2 times the quantity x plus 3 equals 0. So then we have x plus 2 equals 0 and x plus 3 equals 0. So we get x equals negative 2 and x equals negative 3. So as ordered pairs, we have the x-intercept negative 2, 0 and negative 3, 0. We have two x-intercepts here. For our y-intercept, we're going to evaluate the function h of 0. And so this is equal to 0 plus 2 times the quantity 0 plus 3 all over 0 minus 1, the quantity. So this would be equal to 2 times 3 all over negative 1, which is equal to negative 6. So as an ordered pair, our y-intercept is 0, negative 6. Let's get some practice. F of x here, we're going to start with x-intercepts. So here we have where the numerator x plus 6 equals 0. So we get x equals negative 6. So our x-intercept is negative 6, 0. For y-intercept, we can evaluate f of 0. So we get 0 plus 6 over 0 squared plus 0 minus 6, Well, this is equal to 6 over negative 6, or negative 1. So as an ordered pair, 0, negative 1. All right. Number 2, g of x. For x-intercept, that's where we have our numerator equal to 0. So the quantity x minus 3 squared is equal to 0. We have one distinct 0 here. So this would be at x. Well, we'll go ahead and write that out. X minus 3 equals 0. So x equals 3. So we have one distinct x-intercept at 3, 0. And finally, our y-intercept. We have g of 0 is equal to the quantity 0 minus 3 squared all over the quantity 0 plus 1 times the quantity 0 plus 3. This is equal to the quantity negative 3 squared over 1 times 3. This is equal to 9 over 3, or 3. So the y-intercept is 0, 3. All right. Now let's go ahead and talk about graphing. So sign chart and graphing. Actually, before we do, one last thing I wanted to mention on x-intercepts. When we look at x-intercepts here, this has one distinct x-intercept at 3, 0. Similarly to polynomials, where we're talking about multiplicity and bounces or passing through, the same is true for rational functions. This function is going to have a bounce at x equals 3. Okay, now let's go ahead and flip the page. We'll talk about sign chart and graphing. Okay, much like we did with polynomial functions, we have to create a sign chart to show where the function is above or below the y-axis, or where the output is positive or negative. We include anything that affects the x-axis on our sign chart. So for rational functions, we include x-intercepts, but we also include vertical asymptotes. All right, so we'll start with the function f of x. We're going to start by describing the end behavior using limits. Remember, that's that dominant term. This is going to be similar to, well, we have the dominant term in the numerator is x. The dominant term in the denominator is x squared. So we can say that the limit of f of x as x approaches negative infinity is the same as that over x squared, or 1 over x, and that's going to approach 0. So therefore, the limit of f of x as x approaches positive infinity is also equal to 0, making our end behavior asymptote y equals 0. Vertical asymptotes, or infinite discontinuities, that's where the denominator is equal to 0. So let's set that denominator equal to 0. The quantity x minus 2 times the quantity x plus 1 equals 0. We have two vertical asymptotes, x equals 2 and x equals negative 1. Okay. Intercepts, we'll start with x-intercept. So that's where the numerator is equal to 0, where y equals 0. So we have the quantity x minus 3 equals 0. So then x equals positive 3. I'm going to write that as an ordered pair just so that I can keep track of my intercepts. So 3, 0. The y-intercept, we're evaluating f of 0. So this is equal to the quantity 0 minus 3 all over the quantity 0 minus 2 times the quantity 0 plus 1. This is equal to negative 3 over negative 2 times 1, which is equal to positive 3 halves. So as an ordered pair, we have 0, 3 halves. Okay. Now let's go ahead and draw our sign chart. So remember, we're going to include vertical asymptotes and x-intercepts. So in this case, we have two vertical asymptotes, one at negative 1 and one at 2. And we have a x-intercept at 3. Okay. So one way that we can do this is we're going to start with end behavior. Okay, so I'm going to just write a note here. We're going to start with the end behavior. Okay, and just like how we did with polynomials, we would look at the multiplicity of each of those factors and determine whether the function shares the sign or changes sign. Okay, but if the end behavior asymptote is y equals 0, then you can't start with the end behavior because the end behavior is 0. So we can't say that it's positive or negative. So we're going to start with, start with the y-intercept. Okay. All right, so the y-intercept, let's take a look here. We have 0, 3 halves. Well, 0, 3 halves is a positive quantity. So I look at my sign chart here and find the interval containing x equals 0. So that would be this interval between -1 and 2. And I know that that's positive 3/2. Okay? So now we take a look as we move over the x value at 2. So this would occur in the denominator. This factor has multiplicity 1. So that tells me that the sign is going to change from positive to negative over that factor, over that vertical asymptote. Okay, at x equals 3, we're looking for that factor. That's an x-intercept. That x-intercept has multiplicity 1, so that is going to change the sign again. So we know that the right hand is going to be positive. And finally, at -1, so on the other end, that's this factor down here in the denominator, or vertical asymptote, has multiplicity 1, so it's going to change sign over that too. Let's go ahead and sketch this graph. So here we have a vertical asymptote at x equals 2. We'll draw that as a dotted line. And then we also have one at -1. Another dotted line is our vertical asymptote. We've got an x-intercept at 3, 0. We've got a y-intercept at 0, 3/2. And we also have a horizontal asymptote, y equals 0. So I'm going to just draw that as a dotted line as well. Okay. One quick note is that functions will always, or will never, I should say, never touch vertical asymptotes. Remember, it's undefined. However, the rational function can touch a horizontal asymptote and then level off and approach that asymptote as the end behavior. So you can cross a horizontal asymptote. You cannot cross a vertical asymptote. All right, so let's go ahead and graph this. I know that on the left side of -1, the function is going to be negative. So that tells me that just a quick sketch of the function. It's going to be approaching 0 from the left-hand side, and then it's going to also be approaching negative infinity on the left-hand side of this asymptote. So try to draw that nice and curved. Okay. Between -1 and 2, we have that the function is entirely positive, and we can see that here with the y-intercept. So this function is going to be entirely positive and approaching the vertical asymptotes on either end. Remember, as we get close to vertical asymptotes, the function is going to either approach infinity or negative infinity. Finally, after x equals 2, all the way up to 3, it's going to be negative, and once it hits 3, it's going to cross over to positive, and then it's going to level off to our end behavior asymptote. So we're coming out from negative infinity. We're going to come up, hit that 0 at x equals 3, and then it's going to level off and approach that y equals 0. All right, so this is the sketch of the rational function. All right, let's try another. So g of x, describe the end behavior using limits. So this is going to approach x squared over x squared, which reduces to just 1. So that tells me that the limit of g of x as x approaches negative infinity is equal to 1. And the limit of g of x as x approaches positive infinity is also equal to 1. So the end behavior asymptote is y equals 1. Vertical asymptotes is where the denominator is equal to 0. So we have x squared minus 4 equals 0. This factors 2x plus 2 times x minus 2 equals 0. We have two asymptotes at -2 and +2. Okay, so intercepts. We'll start with the x-intercept. And that's where the numerator is equal to 0. So we have the quantity x minus 4 squared is equal to 0. So this is where x is equal to 4. So we have the x-intercept for 0. For y-intercept, we can evaluate the function g of 0. So we have 0 minus 4, the quantity squared, over 0 squared minus 4. Well, this is equal to 0 minus 4 is -4, square root of 16. 0 squared and then minus 4 is -4. So we get a y-intercept of -4. Okay, now let's go ahead and draw a sign chart. So we're going to go ahead and plot our vertical asymptotes. We have one at -2 and +2. We also have an x-intercept at 4, 0. Okay, so because the end behavior asymptote is +1, we know both ends are approaching +1. Over -2 and +2, each of these zeros have multiplicity 1, So that tells us that the sign is going to change over each of these zeros. So over -2, it's going to change from positive to negative, and over +2, it's going to change from negative to positive. Let's do that last check for x equals 4. Finding that factor here, at x equals 4, we see that the multiplicity of this factor is 2, so that tells us that the sign is going to stay the same about that x value, okay? In this case, the x-intercept. So it's going to bounce at that 0. Let's go ahead and sketch a graph here. So we have vertical asymptotes at -2 and +2. We have our end behavior asymptote, y equals 1. We've got our x-intercept, 4, 0. And we've got our y-intercept, 0, -4. All right. We know that the left-hand side, to the left of -2, the function is positive, so it must be up here. So just sketching that, we can see that it approaches positive infinity at as we approach -2, and it's going to approach 1 as we approach negative infinity. In this middle part here, we can see that between -2 and 2, we have a negative, which actually makes sense with our y-intercept, by the way. So this function is going to approach negative infinity on both sides of the y-intercept. Okay. Finally, between 2 and 4, we're coming down from positive infinity. And then we're going to come down and hit this x-intercept at x equals 4, and then bounce, and then approach that horizontal asymptote. So we're coming down from infinity. We're going to hit that 0 and bounce, and then level off and approach that horizontal asymptote. Okay? So this is a sketch of the rational function g of x. All right. Let's go ahead and flip the page. Let's get some practice. All right, so number 3, we have j of x. Describe the end behavior using limits. Well, looking at the dominant terms, dominant term of the numerator is x squared. Dominant term of the denominator, we've got 3 x's. So this is going to approach that of 1 over x. So that tells us that the limit, this is bottom heavy, so limit of j of x as x approaches negative infinity is equal to 0. And the limit of j of x as x approaches positive infinity is also equal to 0. And behavior asymptote, y equals 0. Vertical asymptotes are where the denominator equals 0. We have x plus 4 equals 0. And x minus 3, the quantity squared, equals 0. So then we get x equals -4 and x equals positive 3. For intercepts, we'll start with x-intercept. So this is where the numerator equals 0. So x squared minus 4 equals 0. We get x plus 2 equals 0. X minus 2 equals 0. So we get x equals -2 and positive 2. So as ordered pairs, -2, 0, and 2, 0. So we have 2 x-intercepts here. For our y-intercept, we can evaluate j of 0. So we get 0 squared minus 4 all over the quantity 0 plus 4 times the quantity 0 minus 3 squared. This is equal to -4 over positive 4 times positive 9. So this would be equal to -1/9. Okay, so as an ordered pair, we have 0, -1/9. For our sign chart, we're going to plug in 4 values, so -4, -2, 2, and 3. We know that the end behavior asymptote is y equals 0, so we have to start with our y-intercept. So finding the interval containing our y-intercept is between -2 and 2. The function value is negative. Okay? We know about -2 and 2, the multiplicity of each of these zeros is 1. Okay, so that comes from the numerator here. If we were to factor the numerator, this would be equal to the quantity x plus 2 times the quantity x minus 2. So then we know that the multiplicity is going to be 1 here. So about those 2 x values, the function is going to change sign. At x equals -4, that would be this first factor here. This has multiplicity 1, so it's going to change sign again. But at x equals 3, this has multiplicity 2, so we know that it's going to keep the sign. Let's go ahead and sketch this graph. So we have our vertical asymptotes at -4 and 3. We have our horizontal asymptote at y equals 0. We've got our x-intercepts at 2, 0 and -2, 0. We've got our y-intercept, 0, -1/9. And that's it. Okay, so the left-hand side, we know that the left-hand side left of -4 is going to be negative. So we're going to approach the asymptotes on the negative sides. Okay. Between -4 and -2, we have positive. Then it's going to pass through and be negative and hit that y-intercept. So we're coming down from positive infinity, pass through that 0. It's going to come down, hit that y-intercept. It's going to kind of come back up and pass through that other 0, and then approach positive infinity again. So it passes through each of these x-intercepts. Finally, after x equals 3, the function remains positive, so we've got this behavior here. All right, so let's try the last one for today. Here we have p of x. We're going to follow the end behavior. Dominant term of the numerator is 4x squared, and of the denominator we have x squared. So this is going to approach 4. These are equally weighted. They're both degree 2. So that tells me that the end behavior, so limit of p of x as x approaches negative infinity is equal to 4, and the limit of p of x as x approaches positive infinity is also equal to 4. So end behavior asymptote, y equals 4. Vertical asymptotes is where the denominator equals 0. So we have the quantity x plus 1 squared equals 0. So we get x is equal to -1. For intercepts, we'll start with x-intercept. This is where the numerator is equal to 0. So we have 4 times the quantity x minus 1 times the quantity x plus 3 equals 0. So we have x minus 1 equals 0, x plus 3 equals 0. So we get the vertical asymptotes, or I'm sorry, x-intercepts, x equals 1, and x equals -3. So as ordered pairs 1, 0, and -3, 0. For y-intercept, we are evaluating p of 0. This is equal to 4 times 0 minus 1 times 0 plus 3, the quantities. And then we have over the quantity 0 plus 1 squared. This is equal to 4 times -1 times 3, all over 1, which is equal to -12. So then our y-intercept as an ordered pair, 0, -12. For our sign chart, we're going to plug in our vertical asymptotes and our intercepts, our x-intercepts. So we have -3, we have -1, and 1. We know that the end behavior is +4, so both ends are going to approach +4. At x equals -3, this factor has multiplicity 1, so the sign is going to change from positive to negative. At -1, this factor has multiplicity 2, so it's going to keep the sign. It's going to bounce. At x equals 1, this has multiplicity 1, so it's going to change sign, which follows with our sign chart. So let's go ahead and graph this. Vertical asymptote, we have 1 at x equals -1. We've got an end behavior asymptote of y equals 4. We've got an x-intercept at 1, 0 and at -3, 0. And a y-intercept of 0, -12, which is way down here. So we know that to the left of x equals -3, the function is going to be positive. and then it's going to pass through that x-intercept and then approach the asymptote going to negative infinity. Okay, so this function is going to move left like this, but then as it passes through that x-intercept, it's going to approach the asymptote at x equals -1, going in the negative infinity direction. To the right of the asymptote at -1, we're going to come up from negative infinity, pass through our x-intercept at x equals 1, and then approach the horizontal asymptote y equals 4. So we've got this function, passes through the y-intercept, passes through our x-intercept, and then levels off to y equals 4. All right? So these have been our notes on graphing rational functions. Today we talked about a lot. We talked about end behavior asymptotes. We talked vertical asymptotes or infinite discontinuities. We talked x and y intercepts. We talked sign charts, and we talked sketching the graph, putting it all together. We're going to get a lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.